So I'm going to talk a bit about what we're doing with OpenCAPI, and some background, which a lot of it is in common with the Gen-Z presentation, in common with previous presentations. So you'll kind of see how we're trying to at least address that. So industry-wise, we've got really two significant things that are quite dramatic compared to, like, say, my last 20 years in processor architecture. The last 20 years were spent making our CPUs go from 400 megahertz, I think was the first one I worked on, to somewhere in the 4 gigahertz range. And then, some number of years ago, probably 5 to 6, we capped out on that frequency, and we're having essentially Moore's law pains, right? No greater frequency parts. We are getting more transistors, but those transistors are at the same power that they were in previous designs. And so we end up having this huge problem trying to do everything with general purpose processors. So we've adopted accelerators. IBM just did this joint project with NVIDIA supercomputer. We now have the top 500 supercomputer in the world. And where do all the flops come from? They don't come from the general purpose processors. They come from the accelerators in NVIDIA. Those NVIDIA accelerators, though, need to talk to the network. They need to talk to host memory. And so that's kind of what the power processors become in those systems, is a way to tie accelerators together, tie emerging memory together, and tie networks together. But certainly we have to deal with accelerators and integrated accelerators. The other side of things is memory technologies, right? We now have a long list, as you guys have seen, of different emerging memory technologies. And we need to be able to figure out how to deploy those technologies in an efficient way, in a very dynamic way. And that's a big part of what we're trying to accomplish. So what does an accelerator want to be? And what we don't want it to be is a device that you talk to through a device driver that has high software overheads, that transfers a block of data to the accelerator churns on it for a while, and then sends the data back. That very much limits the ways in which you can deploy accelerators. We need the accelerators to be tightly coupled to the processor, to the host processor, and other accelerators in the system, and able to communicate through shared memory, right? So we want to be able to talk through accelerator to accelerator, accelerator to host, through our shared memory model, just like multi-processor systems talk to each other. So if I got 8 CPUs in a box, you don't need device drivers to talk from one CPU to another. You want to be able to talk through shared memory. So that has implications on how we do addressing. We don't really like I/O MMUs. We like MMUs. We also want to be able to manage cache coherence. Once again, when I share data between 2 CPUs, I don't have to do a bunch of explicit cache flush instructions or things like that. That's sort of 2 decades ago or whatever. We got lots of form factors. We have lots of different accelerators. Different applications require different accelerators, and so we want to have a very fluid, heterogeneous system. The other side of things is data centers want flexibility and openness. People don't want closed standards. They want to be able to go and buy processors from Intel, buy processors from AMD, buy processors from other vendors, IBM obviously, right? And they want to be able to mix accelerators across those ecosystems as well. So proprietary, bad, open, obviously a requirement going forward. So let's talk a little bit about that. So acceleration is becoming commonplace. The acceleration communication wants to be fast. PCIe, people have latencies in the 700 microsecond range, microseconds. That's a lot of time for a processor to be sitting there doing nothing, right? We're trying to execute in a CPU, trying to execute, 4 instructions a cycle, 3 instructions a cycle. Those instructions are 250, they're a quarter of a nanosecond, right? So if I'm sitting there for 1,000 cycles waiting for an accelerator, that could have been 4,000 instructions that I wasted, right? Processors are expensive. We want to get full utilization of them. And if your processor thread's sitting there for 4,000 cycles waiting on memory or waiting on an accelerator, that really limits how well you can ship a little bit of work out to the accelerator and have it back. So we need to make things tightly coupled and low latency. So to get this to happen, though, we need this full industry participation, right? It's got to be. In the past, IBM has done memory in this way, but in proprietary standards. We've done accelerators also in proprietary standards. But we want to be able to have a broader set of memory devices and a broader set of acceleration devices to get tied to. So how do we do this? We were looking at what we had before. So historically, we'd built accelerators using a PCIe ecosystem. And so we started back in Power 8 with doing coherent accelerators on PCIe. But the problem we ran into is the latency of a PCIe stack was much higher than we needed, right? I just said 700 nanoseconds to talk to PCIe, which is just tremendously too long. So we also needed to have a way to do coherence. PCIe doesn't have a typically good coherent mechanism in it. And to do things involving coherence, you need virtual channels. Those are expensive in PCIe ecosystems. You also need different types of formatting and templating. So we started with a clean sheet design that we based around our previous work in attaching low latency memory devices, and also the previous work we did in accelerators to build this device where you could have a very thin layer in the accelerator that would talk across an open interface with low latency. We had to go clean sheet though, because if you looked at the way the PCIe packets were made, the way they were encoded, that was sort of incompatible with what we wanted to build. The one interesting point though, just a side note, is the electrical standard with PCIe is actually fairly reasonable. It's a differential signaling interface. It runs at fairly high frequencies. And we've found that the electrical signaling with PCIe is actually quite compatible with OpenCAPI. So a lot of the vendors we've talked to currently have a PCIe-based NIC, whatnot, are able to take that same I/O interface that talks PCIe and have it run higher frequency and then talk OpenCAPI. So electrically, PCIe is pretty good. The problem we had with it really was how are the packets formatted and how are those packets aligned? And a little low frequency, but if we bump the frequency up, reorganize the way the packets work, quite a bit of an improvement can be made. That said, so that's how we create the OpenCAPI bus, open standard. So addressing, this is an interesting discussion, especially when you talk about how you do virtualization and integrate accelerators into your work. So what we want the accelerator to see is just what a processor sees, which is an effective address or a virtual address. So when you dereference a pointer in your program, that the actual physical location has been hidden from the application. Those pointers run in a true virtual memory system. So if I want to dereference a pointer, it might be on disk. It might be paged in memory. It may not be paged in memory, but it's just a pointer. So we want the accelerators to be able to operate using those same virtual addresses that the processors need. Now today, with an I/O type of infrastructure, you often need to make calls to the I/O MMU to set up translations for the I/O device. And those pages need to be pinned. And so the software overhead to go give a block of data to a DMA engine is quite prohibitive. So we want to be able to have the processor use the same page tables as the accelerator. To do that, though, we need to be able to handle I/O and validations, translation and validations, and all these things. So that's a big part of what we're building in the OpenCAPI protocol, is a way to have all those things be straight virtual addressing. And what we do is we actually do translation from the virtual address to the physical address in the host bridge. So from an accelerator's perspective, all it sees is program addresses. We hide what the actual physical address is from the accelerator, and that enables security. It enables really simplified translation shootdowns and a variety of things. But that's a big part of the programming model, right? Which is we want a CPU that's executing code. We want an accelerator that's operating on those same shared data structures. We want those all to be tied to this same sort of flat memory space, right? So processor going to system memory, accelerator going to system memory, looks the same. We also need to integrate device memory into that same flat address space, right? So if you're writing code and you want to target an operation into device memory, you want to target it into system memory, those should look the same to the programmer. So we need to provide flat virtual address space and able to integrate device memory into the same system map as the memory. So this is kind of how we see this heterogeneous world working. You can also think about multiple kinds of memory. There could be DRAM-based memory in the system. There could be phase change memory, any variety of different memory devices. all need to map into the same shared address space. So this one, I guess I have a little bit of passion about in memory in systems. So the way we attach memory historically in like a typical industry system is with DDR memory. And direct attached DDR memory is really a horrible interface. It runs at low frequency, right? If I'm talking about DDR, it's running maybe at 2500, 2.6 gigahertz. This is an extremely low frequency compared to what we get with differential signaling. In the differential space, we're at 25 gig today. So we're running like 10 times faster device to processor interfaces compared to DDR. The other problem with DDR is it's not very scalable. As we try and put more memory devices on this bidirectional bus has more loads, it runs at lower frequency. The DDR interface is also it doesn't hide the memory device from the processor. So if I put DDR4 memory on a processor, that has a very specific electrical standard timing interface. If I want to go plug DDR5 memory into a processor, I have to have a totally different electrical standard. So there's incompatibilities. And what if I want to plug phase change memory into that processor slot? Now I have to come up with some, I'm going to call it slightly hacky approach to try and integrate different memory latencies into this very, bare DDR protocol. And so the DDR protocol has big problems. It's too slow, and it's too tied to the device media. And so what we need to do is we want to run it on differential signaling, just like every other interface in the processor is moved to other than memory. So what this differential signaling gives you, it gives you a massive increase in bandwidth. And it also enables you to develop a protocol that's memory agnostic. So I do a load out to memory, and when the data comes back, it might be an out of order, it might be at variable latency. It comes back, and I didn't care whether or not it was DDR4, phase change memory, graphics memory. The load went out to the network, right? So attaching memory with differential signaling is tremendously the right way to go. And what we've done here is we basically have made a variety of memory form factors. This connector you'll see later in a little bit, as are the form factors. But we built a buffer chip. You can think of this as equivalent to like an LR buffer chip, but instead of talking DDR out one side, it talks differential signaling. Then it talks to DRAM devices, and we have different varieties of these. We have short ones to fit in little 1U servers. We have tall ones, which have higher RAS or redundancy features. It could be phase change memory, storage class memory. It could be any variety of things. But one thing we've done, and this is something that you'll see that's a little different from the next presentation, is we've optimized this for extreme low latency. And by extreme low latency, we have about a 5 nanosecond delta between using direct attached memory or this SerDes-based memory. And that's accomplished with a lot of tricks in the protocol that we've developed on previous buffered solutions, right? And that's a significant difference from other protocols. Now that said, that means the protocols themselves are very much associated with a direct host attachment, right? We don't have switching capability in OpenCAPI. This is, I can plug a DDR memory in with minimal latency add, right, in the idle case. So 5 nanoseconds in the idle case turns into a positive latency in the loaded case, right, because I'm able to put that much more memory behind my processor. So this is pretty important with what we're doing here and a big step at what's differentiating future IBM systems. And we really like to get the rest of the ecosystem to pick up on this device because it really is a way to build better memory subsystems. So what are the different types of paradigms we see? We kind of already talked about this, but we want to be able to do direct DDR replacement. So instead of having DDR DIMMs, we'd like to plug in those other DIMMs, memory DIMMs you saw there. Those enable this to be a generic agnostic interface. So that same processor, I can now plug in storage class memory. Storage class memory with different memory latencies, different ordering rules. One other thing I should mention about storage class memory and this interface is that writes in this OpenCAPI interface are explicitly acknowledged, right? So when you send the write to the device can then acknowledge when that write completed. This can then be tied into your I/O libraries on your processor, right? Because that's typically how this persistent works, is you do a write, a store rather, you execute some flush operations. When those flush operations complete, then you know the data is secure. But with traditional DDR interfaces, and this is especially true in some of these flash-back devices, you do a write to DDR, and it just says, okay, yeah, there's no acknowledge, right? There's nothing in the DDR protocol that enables you to say, this is when my write's secure. There's no explicit acknowledge. It's just you send the data, and if there wasn't an error, life is good. The problem is, you don't know if it really got there or not. And so since we have an explicit write acknowledge, that enables much more sophisticated persistence mechanisms in the memory. And there's nothing to say that the OpenCAPI devices couldn't have tiering. And so we've looked at some devices where one processor interface talks to DDR as sort of a cache of memory that lives behind it, right? So you could tier things. You could also bridge to other memory technologies here, right? You could come out the back of this. You could have a Gen-Z connector just to try and talk about things, right? So you've got your low latency connectivity to your DDR, and then you could have the back of that go off talk to other memory standards, right? So that's kind of how we see that. This is a little bit of a rehash of what we already saw, but we have host processors, we have accelerated processors, we have accelerator memory. This could be HBM in the case of like a GPU. We have host memory, which is, and this is all shared. We can issue atomic operations. Those are supported on these protocols. Different threads can all communicate sort of in one happy family. Accelerators, and this is kind of interesting, is that memory devices, as they become more sophisticated, want to be more than just slaves, right? If I have a device that maybe is doing compression or is mixing, it wants to be a memory slave some of the time, but it also wants to master operations, right? I think we saw some of the earlier presentations where you put a device memory out there, maybe it has the ability to compress and decompress data as it goes. But to do so, maybe it needs to talk to the processor to learn encryption keys. Maybe it needs to figure out what decompression dictionary needs to be used. And so you get this hybrid approach where you have a memory device where it looks like loads and stores, but it's sort of a smart memory device. It needs to be able to initiate accelerated operations, right? It needs to master commands. And so that's another thing you don't get with the DDR interface, is you don't get the ability to have the accelerator generate an interrupt. It can't issue a load. It can't be its own master. And so the nice part here that we merged sort of the OpenCAPI memory interface with the OpenCAPI accelerator interface is that it can be an accelerator and a memory device at the same time. And a lot of times the accelerator devices have memory behind them. And so this enables a wide variety of paradigms on, what is my accelerator doing? Maybe I'm doing just simple offload where I go tell it to do work, it does the work. But potentially it's sitting on the network, right, which enables it to do compression, decompression, encryption. It may have its own memory on the device. If it has its own memory on the device, it's maybe accessing that concurrently with the other processor. So these are the kind of devices we really want to build in these new emerging spaces. Signaling technology here, I'm just a little comment here. Right now we're at 25 gig, which is what our processors today support. We have a roadmap going out to about 2021 currently, which shows us going 32 gig, 56 gig are the type of frequencies we're looking at doing in that 21 kind of time frame. The other thing that's important is the standard here is this is a fairly easy to digest memory standard. It matches Xilinx FPGAs, SerDes. We haven't come across a single vendor yet who can't support this differential signaling technology. It also has a lot in common with the next presenter. It's common with them. The other thing to mention here is we do have work groups to help defining these things. One of those things we use in the work group is a common 25 gig signaling. We use this signaling for SMP Interconnect. We also use this same signaling standard for our NVIDIA NVLink attach. So same 25 gig, we actually have currently 3 personalities on our processors. We can talk OpenCAPI across those links. We can talk NVIDIA NVLink, and we also use the same protocol for our processor interconnect. And this is kind of an interesting thing in that the silicon area is mostly dedicated to the SerDes signaling estimate. The actual thing that decodes what a translation block looks like is pretty tiny. And so far we've been successful with having We have 3 technologies on this protocol, and it's really quite tenable. It's not a significant tax on our processor chip. So let's kind of look at what a OpenCAPI system looks like if we think about our future. We have a derivative Power 9 system that will look just like this. And what is that? Nearly all of my signal IOs, or ideally all of the signal IOs coming off the processor, are this differential signaling. And that lets us build a very composable system where maybe somebody wants to build a system with just lots of DDR bandwidth, right? Some HPC lab, they got a bunch of codes, they care only about memory bandwidth, they dedicated all these 25 gig signaling things for memory, and they have a terabyte per second of memory bandwidth, right? Per socket, right? 10x factor over what you can do today approximately. That makes their codes run 8x faster. Big TCO win for those organizations. Let's say you want to run a database that wants lots of persistent memory, right? So you dedicate half of these IOs to persistent memory, half of them for DDR, right? Depending on what exact ratio you need, it lets you build exactly what you want. You can use some of these lanes for accelerators, right? So it lets us take one processor chip, one host silicon, and then compose, picking up different accelerators, different memory, and tie them all together, right? So that's what we like a lot as CPU designers about these sort of universal interfaces, is it lets us build a variety of optimized systems with different components to them. This is all tied together with the things we just talked about. A little bit of roadmap here. OpenCAPI is kind of an interesting name. CAPI was the name we used for our proprietary accelerator attach going back to Power 8, which was tunneling these coherent operations across PCIe. That we saw the latency was kind of painful. We really needed to get better latency. That's why we transitioned to the direct 25 gig signaling. We made it open as well because the particular thing we had with CAPI was a little complex and we needed to move IP from the accelerator to the hosts. So we made our host do more work, the accelerator do less work, and then we made it open. And that's what we have today, Power 9. We've been shipping these for not quite a year, but close to a year, and that has 25 gig accelerator interface. For a Power 9 follow-on, we will extend our OpenCAPI capability and we'll add this low latency memory interface. The Power 9 you see here, for its memory, we have 2 versions. One of them is just traditional DDR. The other one is our proprietary buffered memory solution. So that same technology in our proprietary buffered one is what we've put into the OpenCAPI standard, which is what this 3.0 version is, and that's what we'll have our next chip here. But memory bandwidth-wise, we're talking a standard DDR4 memory subsystem based around OpenCAPI. We have like 400 gigabytes per second of sustained bandwidth. So a massive bump in bandwidth to support accelerators, high-performance computing. So big bump in bandwidth. And this is something where we'd like to see other vendors pick this up, right? Or even accelerators, right? If you want to put a lot of memory behind an accelerator, use this OpenCAPI memory interface. So that's what we have on the short list. Talk a little bit about what these things look like. We found that running this high-frequency interface, we typically want to do through cabling solutions. The motherboard, if you're going to run 25, 32, 50 gig, the material becomes more expensive. And so we're actually kind of trying to border between, do you want to do all cabled solutions, right? That way your motherboard can just be power and ground. We could take these cables off the top of a module perhaps and have them go directly to accelerators. So today we're pretty centric around cables. We have a short reach in the motherboard from the processor socket. Then we have these jumper cables that can go plug into the card. To make this sort of simple, the first prototype cards we did, we put them on a PCIe bus. We get power and ground from the PCIe bus. We plug it in the box. We run one of these jumper cables to run the 25 gig over. So what do some of these parts look like? This is an FPGA card from Alpha Data. This particular one had the connector on the side. Production versions of this have the connector at the back. But essentially, it looks just like a PCIe card, except it has this 8 lanes of 25 gig going into the side of it. And this is kind of an interesting card that Mellanox has built, which is a hybrid device. And so it takes their standard NIC, which continues to use the PCIe bus, but then it has a parallel FPGA on the card that talks OpenCAPI. So you kind of think about this as you're able to take your NIC where the data flows to the NIC, and the NIC can either route commands to the processor, but it also can route commands directly to an FPGA. And that FPGA you can think of as an extension of the processor, right? It's tightly coupled coherently with the CPU, and this enables it to run packet inspection things as if you had a little algorithm moved onto the card. So this does show kind of how you can sort of hybridize different devices. This has InfiniBand Ethernet merged with OpenCAPI, right? So different networking solutions can merge with OpenCAPI to sort of build these devices together. Just to comment, the 25 gig stuff runs clean. There's no reason it shouldn't. It's a fairly standard interface. But yeah, we do have these in the lab. There's probably actually about 4 different FPGA card variants that are OpenCAPI cards that people can buy. So we have a consortium for OpenCAPI. The president, are you still the president, Myron?
Yes.
Raise your hand. There's the president. Elected, yeah. Anyway, try not to talk about that. All right, so we have, we're trying to proliferate this, working to get members to help build accelerators and adopt the standard. And you can join today. There's different membership levels, like many of these consortiums, and feel free to talk to Myron about it. So that's what I have, and now we're going to switch to our next presenter. Thanks.